This podcast will do a little bit of review about the kinetic molecular theory, and then we will learn two concepts and practice two sample exercises: what is root mean square speed and how we can use Graham's law of diffusion effusion. So it's a very quick review because we did this previously before the end of the first semester. We know that the kinetic molecular theory assumes that gases are constantly, rapidly, randomly moving molecules or atoms. The size of those particular particles is pretty much nothing compared to the volume of the container, and that they have no attractive or repulsive forces between each other. You have elastic collisions between molecules, but the total kinetic energy will not change as long as you keep the temperature constant, and therefore the average kinetic energy is directly proportional to the temperature. So it gives us an understanding of how pressure and temperature work on the molecular level. You get pressure every time a particle collides with the wall of the container. And if they're hitting often and they're hitting with greater force, then that means higher pressure inside. So gas molecules as a group have an average kinetic energy, but each molecule will have its own unique energy. There's a spread of individual energies of gas molecules in a particular sample of a gas. But as you know, increase the temperature, that average kinetic energy will also increase. Now this graph I have on the next slide in a slightly larger version, but recognize that we're looking at two different containers here. The one in red, signified by the graph in red, is the one at a higher temperature, and the one in blue is one at a cooler temperature. Remember, the average kinetic energy of the molecules won't change with time, as long as you keep the temperature constant. So what can explain the differences here then in the fraction of molecules, that's the y-axis, that have a particular speed, that's the x-axis. And at first you think, oh, this red bell-shaped curve is lower than that of the blue, therefore its molecules must be moving more slowly. But what we're saying is there's a range in both of these graphs of molecular speeds. Some within the blue and the red sample are moving slowly, some are moving fast, but there's a range. What we're saying is if you find the peak of this graph right here, the one at the hotter temperature, it's shifted more to the right, meaning that more of its molecules are moving faster than the fraction of molecules that are moving at that same speed in the colder substance. So that's how we understand this relationship between temperature and your molecular speed and kinetic energy. Now let's take a look specifically at that funny symbol there, that root mean square speed. If I could actually get this thing to move. Let's try this. There we go. So as the kinetic energy increases, the gas particles are obviously moving faster. But if you could calculate the average kinetic energy and find a molecule that has that average kinetic energy, it would have what we call the root mean square speed. Average kinetic energy is related to the root mean square speed, and here's our formula for kinetic energy: 1/2 times mass times velocity squared. Let's take a look just very briefly. If you kept the temperature constant and let the volume get bigger, since the temp's not changing, that root mean square speed is not going to change. But since the walls of the container are farther away from the gas particles, it takes longer for them to hit those walls. They hit less frequently, and therefore the pressure decreases. Also, they would be hitting with less force. If you increase the temperature, though, and keep the space, the volume, the same, now the average kinetic energy of the gas molecules is going to increase. There are more collisions with the wall. With greater force, pressure inside increases. So once again, this first equation is the average kinetic energy. The second equation is the root mean square speed. So root mean square speed is equal to the square root of 3 times the gas constant times the Kelvin temperature, all divided by the molar mass. And since that molar mass is at the bottom, if you're comparing two gases that have the same temperature, but one is heavier, then it's going to have, since this is a denominator, it's going to have a slower or lower root mean square speed than the lighter gas. And that can have some very interesting practical applications, which I'll come to. So let's take a moment and look at a graphical representation of that. The different colored lines show different elements with different molar masses, and the hydrogen graph in orange is shifted farthest to the right because it has the lightest molecules. It has therefore the highest root mean square speed compared to more heavier elements or compounds that can be in gaseous form. Okay, so let's do a root mean square speed problem. Hope we don't have any formatting issues. So it says find the root mean square speed of a nitrogen molecule at 25 degrees Celsius. Pretend you're in test mode. Change the 25 to Kelvin. Instantly go find the molar mass of nitrogen, and then you'd refer to your equation sheet to find the formula for root mean square speed. Here they are, changing the temperature into Kelvin. The molar mass in grams per mole of nitrogen is 28. Let's take a look at why you have to change that into kilograms. When you use the root mean square speed, you're going to be using, you're going to be measuring energy in terms of joules. And joules imply that you've got a kilogram of mass spread out over a square meter that's accelerating at a rate per second per second. So what I need to condition you to understand is if they give you the mass in grams, divide by 1,000 to turn it into kilograms per mole, because that's the value that must correspond to the use of joules in an energy value. So here's my gas constant, 8.314 joules per mole Kelvin. Here it is with all of the units substituted in. Don't get too hung up on those. Let's take a look at where they go when we actually plug them into the equation. So the root mean square speed is the square root of 3 times the gas constant times the temperature in Kelvin divided by the molar mass given in kilograms per mole. If you take a close look at all of these units, these kilograms will cancel out. This Kelvin is basically on a denominator, so it would be canceling out that Kelvin, excuse me. Let's see what else needs to cancel out. These moles will cancel out. So you're kind of left with this meter squared, second squared, but remember we're going to take the square root of that, so it ends up being just a speed, meters per second. So what we're looking at here is nitrogen makes up almost 80% of the air you just took into your lungs. Those nitrogen molecules at that temperature are moving over 1,000 miles per hour. Kind of a cool thing. So that's root mean square speed. Now let's take a look at what Graham's law of effusion, or sometimes called law of effusion-diffusion, is, and how it can be utilized to find something like the molar mass of an unknown gas. So as you know, as kinetic energy increases, the velocity of a gas molecule will also increase. Effusion is officially defined as trap a bunch of molecules inside a little container with a hole to escape from, and over time, let's say that hole was in the neck of a balloon would deflate due to effusion. And you can quantify the rate at which these molecules or atoms are escaping through that little hole. Notice that if you were asked to give a qualitative description of how come the helium balloon deflates more quickly after a few days compared to a nitrogen balloon, is because the helium weighs less. It has a lower mass. So it's going to end up looking smaller 2 days after you go and buy your happy helium balloon at the county fair. Now this is the Graham's law equation. And first of all, let's decode all the symbology. 1s and 2s mean gas 1 and gas 2. R stands for rate. So if you know the ratio at which one gas effuses compared to another gas, you can set that equal to the square root of the inverse, be careful to do that, of their molar masses. So if you have a higher root mean square speed, the molecule will be hitting that little hole that it's going to be effusing through more likely, and so therefore that's why the helium balloon is deflating faster. So let's put this equation, R1 over R2, equals the square root of the molar mass of gas 2 over the molar mass of gas 1. Let's put that to work. Now there's a happy application to Graham's law, and let's decode this question. An unknown gas composed of homonuclear diatomic molecules means it's a 2-atom molecule and the 2 atoms are the same. That's what it means. So an unknown gas will effuse, escape through a hole, at a rate that's only 0.355 times that of oxygen at the same temperature. So first logic question is, if it's only 0.355 times as fast as oxygen, is it going to be heavier or is it going to be lighter? Okay, I hope you said heavier because it's moving more slowly. What we want to do is calculate the molar mass of that unknown and then identify it since we know it's a diatomic molecule. So I pull out my Graham's law equation. Let's decode it. They decided to let the unknown gas be identified as X. So you could have this set up with X over O2 or O2 over X. Just don't forget that it's the square root of the inverse of the molar masses. So don't get those two mixed up. That's the most common mistake. So how you would say this in English is the rate at which gas X diffuses compared to oxygen is equal to the square root of the mass of oxygen over the mass of X. And that's what we're trying to find out. So don't get worried here. You'll be able to cancel out a lot of this stuff. So first thing is the rate at which X diffused relative to oxygen was 0.355 times that of oxygen. So if this is the rate of X equals 0.355 times the rate of oxygen, let's rearrange that to show the ratio of X over oxygen's rate. And that equals 0.355. Now we've cleaned up that side of the equation. The only unknown is what's the molar mass of the unknown gas? Well, it would be equal to the square root of the molar mass of oxygen, this time it's the inverse, divided by the molar mass of the unknown gas, which is what we're shooting for. Do a little math to clean that up. Square both sides. So here they've squared both sides, but they've flipped it over just to try to mess with your head. And we can square 0.355, that equals 0.126. So therefore, the molar mass should be equal to 32 divided by 0.126, and there's the molar mass of the unknown gas. So that's not what the problem wanted. It wanted you not only to get the molar mass, but to identify it. So you have one last little step. There's no gas on the periodic table that weighs 254 grams per mole, but it was diatomic. So if I divide that number by 2, I would get 127. And the only unknown gas that could weigh that much is good old heavy iodine. So what's interesting about the Graham's law is that it can be utilized to figure out the molar mass of an unknown gas. This is a happy application of Graham's law. I'll talk more about it tomorrow. But the sad application of Graham's law is found in a little sidebar in your textbook, so please go and find that. Because isotopes of uranium, 235 and 238, can diffuse through space at different rates, 238 being slower than the uranium isotope of 235, you can separate those two isotopes by just using the fact that they move through space at different rates at the same temperature. And one of those isotopes is the form that's necessary to build a critical mass for a nuclear bomb. So I would strongly recommend that you look up the section about gas centrifuges, and we'll discuss that a little bit tomorrow in class. So that's the application of Graham's law. Here's another derivation of the Graham's law utilizing the root mean square speed equation. I'm not worried that you get the derivation, but that you understand when to use it, how to know when to use Graham's law, and recognizing, of course, that lighter gases are going to be effusing more quickly than heavier gases. We will pick up tomorrow to discuss diffusion and what is the mean path. All right, I'll talk to you guys later. Bye.